professor at Centro de Matemáticas in Montevideo. He participated at Impasse of Yasser on the periods of the Copales. Well, Martin is a genuine representative of the Uruguay Mathematical School, and his work is very much inspired by the contribution of Lebowitz and Magnet. Well, he's very well known by his proof joining with the results of the Palis conjecture on dichotomy between hyperbolicity and tangencies. And well, he continued on this line of research. He has also contribution in topics of pattern hyperbolic dynamics, sparsity geometry, homeomorphism, but probably it's much better to listen to Martin than me. Martin.
Thank you very much, Lorenzo, for the introduction. And I wish to thank the organizers for this invitation. It's a great pleasure to be here in this beautiful city and this beautiful Congress. And I also wish to thank you for coming today after last party. So what I'm going to talk about is a journey on global dynamics. So I won't give a complete description of global dynamics. I just focus on some aspects of it. And but let me start by saying the thing. The sentence knowledge is achieved by approximation. And what it means is that, it means what it means, but that knowledge is achieved by step. Although Gunther Ullmann told us the other day that that invisible, we can turn objects invisible, or that that we are meeting science fiction, but we are not still in the like in the Matrix movie where we can learn kung fu just in a second, right? So, but besides that, this is something that we do usually in mathematics. We learn it just in the beginning of calculus, that to get some information from a function, from a map, we take the linear approximation, and we can take information from the linear approximation to know what happened with the map. And this is what we do in mathematics many times, and will be our leitmotif in this talk, that to understand dynamics, we will approximate it by another one to get some information. Okay? So let me start with our setting. So M will be a compact Riemannian manifold, and we will take a map which is a diffeomorphisms. And what's our goal is to understand the long time or asymptotic behavior of orbits in the past and in the future. And also, let's denote by diff R of M, the set of CR diffeomorphisms, and do it with the CR topology. And our goal here is to understand the dynamics for most systems. It's impossible to understand the dynamics of all systems. It's impossible to classify them, but at least we would like to understand the dynamics for a dense systems or a generic or residual set of systems. And this is what is called global dynamics. To understand this, the dynamics for most systems here. This is just a part or a field inside dynamical systems. There are many other fields like conservative dynamics, Hamiltonian dynamics, etc. This is just a field that we are going to discuss. Usually we say it also it's dissipative because we don't ask to conserve any quantity or object. Okay. So what are the basic problems or questions that you may ask is to take a system and you say, well, has any periodic point? And if it has, how many? Has attractors, and an attractor is just you have a system and you want a set that attracts a neighborhood of it. However, the irreducible components may be like when you are in the ergodic theory, you look for the ergodic components. Here we look for some subsets of the dynamics that cannot be discomposed into disjoint invariant sets or something like this. Stability. Stability means, what are the systems or which are the systems that are the same after perturbation, that has the same dynamics, the same properties for any system nearby? Or what can we do when you have a system and we perturb it? What kind of dynamics we can have? Maybe we can classify them. I don't know. There are many basic problems about it. But so in dynamics, or usually is something, what it happens, what we know or what we understand, we say that is simple. What we don't understand or what we don't know, this is complicated or complex. So let me start with something that was like 50 years ago, what was simple and was complicated, and in some sense it's something on like linear versus nonlinear. And so let's have the following. Let's say that we have a square in the plane, and we have a map that will map the square into something on the plane, and on the left we will have the linear version, on the right we have the non-linear version. And what it happened is that, so it takes the square, squeezes in the horizontal and stretches in the vertical. So on the left is just this, but on the right, what happened is that we turn this rectangle and put it on the original rectangle like this. This is the one in the right is called the Smale horseshoe. And if we look to the set of points that remains in the original rectangle, the red one, we have the following. On the left, we have just one fixed point. The blue line here are the points that stay in the rectangle for backward iteration, and the red one is the set of points that remains in the rectangle by forward iteration. So the points that remains for all time in the square, in the rectangle, is the intersection of these two, and it's just a fixed point. On the other hand, in the right, we have a contour set of lines, blue lines, that are the points that remains in the rectangle by backward iteration, and the red ones are the set of points that remains in the rectangle by forward iteration. So, and the set of points that remains for all time in the rectangle are the intersection of these two sets of Cantor lines. It's a Cantor set. And the dynamics here is really complicated. We call it chaotic, and it's the same space as the space of flipping a coin. So just here in the left, we have that the blue line. If we take points in the blue line, by backward iteration, we'll get closer, and points in the red line here, by forward iteration, will remain closest and tends to 0. And the same happens here. If we take 2 points in a blue line, by backward iteration, we'll get closer and closer and closer, and points in the red line will get by forward iteration closer and closer. So when we have, like in the square leg, we have a fixed point. Okay. Here we have a fixed point. Here are the set of points that in the past converge to this fixed point, and the one is in the red by forward iteration converge to this point. The blue one is called the unstable manifold. The red one is called the stable manifold. And there are submanifolds of the manifold M. If we are in dimension 2, they are curves. And then these curves, or manifolds, may go around the manifold, and we can have an intersection between these two. And since they are this has complementary dimensions, we may have a point here in the intersection, and it might be transversal intersection of these two curves or two manifolds. And when we have this kind of figure, we have immediately a horseshoe. We may find a rectangle like this that is mapped in the other rectangle by some power of our original map. So when we have a homoclinic intersection, then we have a very rich and complicated dynamics. We have the Smith horseshoe, and we have so infinitely many periodic points and so on, and positive entropy and so on. So the first result that I want to mention is something that we did with Enrique Pujals. This was in dimension 2. Then it was done by Bonatti, Gann, and Wen in dimension 3, and by Sylvain Crouvisier in any dimensions, that there exists an open-ended set H in the space of C1 diffeomorphisms, such that if you have F that belongs to H, then either F has a very simple dynamics, and this, what it means is that we have just finitely many periodic points, and any other point will converge to some of these periodic points. So this is very simple. Just if you want to have an example, a very simple example of this, takes the sphere, and it is then what is called the North Pole, North-South dynamics. The north is fixed, the south is fixed, and every other point goes to the south in the future and goes to the north in the past. So this is what we call a Morse-Smith system. It's very simple. Or F has a transversal homoclinic orbit, and so it has a very rich dynamics. And in some sense, this means that if you have positive entropy, it's because you have a homoclinic intersection. And if your system has zero entropy, then it is very simple. It's like a Morse-Smith. No? The Smith horseshoe came in the beginning of the 60s, and it was the starting point for hyperbolic theory. So at the beginning it was very complicated, but so this was the starting point of hyperbolicity, and this means the following: when we have a diffeomorphisms, a compact invariant set, It's called hyperbolic. If we have two invariant, we can decompose the tangent bundle over the compact set lambda into two invariant subbundles, ES and EU. And there exists a constant C and lambda less than 1 such that the norm of df n to the restricted to S is decreased exponentially fast, and the norm of vectors in EU decreased exponentially fast in the past. And this is like in the horseshoe. The ES correspond to the horizontal direction, and the EU correspond to the vertical direction. Okay. So let's also define an important set where the dynamics take place. It's called the recurrent set. So we say that an epsilon chain from X to Y is a sequence of points, x0, x1, xn. x0 is x, xn is y, such that the distance from xi plus 1 to f of xi is less than epsilon. So this means that we can go from x to y, not by an orbit, but like an orbit with jumps. We start with x, we go to f of x, we jump epsilon, then we have x1, then we iterate x1, then we jump epsilon, and so on. Okay? So, a point x is called chain recurrent if there exists an epsilon chain from x to x for any epsilon. So this means that we can go from x and get back to itself by an epsilon chain for any epsilon positive. And R of f is the set of chain recurrent points. And when we have 2 points in the chain recurrent set, we have a relation, which is an equivalence relation. We say that x is equivalent to y if we can go from x to y by an epsilon chain, and from y to x with an epsilon chain for any epsilon, for any positive epsilon. This is a equivalence relation, and C of x we call the chain recurrent class of x, is the set of points that are in the same class of x. So we say that with a map F, a diffeomorphism F from M to M, is hyperbolic if the chain recurrent set is a hyperbolic set. And there's an important result here by Smale that if we have a hyperbolic system, then we have finitely many chain recurrent classes, and they are very well understood. They are homoclitic classes. They have Markov partitions. We have models of it with subsheets of finite types and so on. So this is really understood, like in the one of the chain recurrent classes could be like the Smale horseshoe. And moreover, it is stable. If we take diffeomorphisms near F, then we'll have the same properties as F, and will be also conjugated to it on the chain recurrent set of F and the chain recurrent set of G. So at the beginning, hyperbolic seems to be very chaotic and very complicated. It's still of course very complicated, but we understand it very well today. Right? So it's our model for chaotic systems. It's expansive and so on. So, but we really understand it very well today. And here is one of the landmarks of this theory, which is a theorem of Magnet in the 80s. It says that if we have a system and it is C1 stable, that means the dynamics of any diffeomorphisms nearby F is equivalent, or is conjugated to F, then F must be a hyperbolic system. So, after we understand hyperbolicity, now hyperbolicity becomes simple for us because we know and we understand. So, what is next? What are the complicated dynamics? So we have two abstractions for hyperbolicity. The first one is what is called homoclinic tangencies. So here we have a fixed point. Here we have the unstable manifold. Here we have the stable manifold. And these two manifolds have a non-transversal intersection. So what happened with this point? If we take this point, by forward iteration we'll converge to this fixed point, and by backward iteration we'll converge also to this point. So these points and these points are in the same change recurrence class, but cannot be hyperbolic because in this point we cannot have two directions which are invariant by the diffeomorphisms. Indeed, what happened is that when we have a homoclinic tangency, the two directions that we have here get mixed. Okay? So the homoclinic tangency, in some sense, mix directions. So this is one of the obstructions to be hyperbolic. And also, what we have is a heterodimensional cycle. So we have here two fixed points, this one and this one. This one has a stable manifold of dimension 2, which is this plane, and a stable manifold of dimension 1. Here we have another point, but now the stable manifold of these two, the stable manifold of this point has dimension 2, and the unstable manifold has dimension 1. So the unstable of this one and the stable of this one intersects, and this may intersect transversally. But on the other hand, the unstable manifold of this point intersects the stable manifold of this point. This intersection is not transversal. Okay, this is one dimension, and this is one dimension. But anyway, this point, you see that by forward iteration converge to this, here by backward iteration converge to this, and here we have a point that by backward iteration converge to this, and by forward iteration converge to this. So this point, and this point are in the same change recurrent class, and cannot be hyperbolic because what happened is that this direction, it is invariant, but if we are in the same chain recurrent class, this direction is always expanded, or it's always contracted. That we cannot have a mixed behavior of some invariant direction in a change recurrent class if it were hyperbolic, or it's always expanded, or it is always contracted. But here we have a point where it is expanded, and here we have a point where it is contracted. So it cannot be hyperbolic. So this is an abstraction. And there is a conjecture of Jacob-Pallis in the 80s that says that any diffeomorphisms F can be CR approximated by one diffeomorphism such that or has a heterodimensional cycle, or has a homoclinic tangency, or it is hyperbolic. So what the results that we have in this direction with Enrique Pujals, we proved that the conjecture is true for C1 diffeomorphisms on surfaces. So if we have diffeomorphism F, always we can approximate it by one diffeomorphism that has a homoclinic tangency, or by one which is a hyperbolic diffeomorphism. And so this is in dimension 2. And Sylvain Crevisier and Enrique Pujas has very nice results recently, which says that if we have a diffeomorphism F on any manifold, on any dimension, then can be C1 approximated by one which has a homoclinic tangency, or a heterodimensional cycle, or it has finitely many hyperbolic attractors with open and dense basins. That it means is that it's essentially a hyperbolic diffeomorphisms, but it's essentially just what we know that the chain recurrent classes that are attractors are hyperbolic attractors, and this attracts almost every point in the manifold. Almost every point in the manifold will converge to one of these hyperbolic attractors, and so we can say that we understand the dynamics here. So, but there is a very nice way also to understand the dynamics in general. This is a very nice and general theorem, Conley Theorem. So it says that take any dynamical systems, and it says that it always exists a Lyapunov function. There exists a continuous function phi from M to 0, 1 such that it decreases along trajectories. Okay? So phi at f of x is less or equal than phi of x for any x. But it is equal, phi of f of x equals phi of x, if and only if x is a chain recurrent point. So if you are not in the chain recurrent set, phi is strictly decreasing along orbits. Okay. And if we have two different chain recurrence classes, then phi distinguish between both. Okay? And if we take the image of the chain recurrence set, this is a compact set in 0, 1, and it's totally disconnected. So this is a Lyapunov function, okay? It's a function that decreases along trajectories. It's constant on the chain recurrent classes. And in some sense, order our dynamics, says how the dynamics goes. The thing is that, the thing is that we don't know how so this is a compact and totally disconnected set, but it could be like a Cantor set. For hyperbolic dynamics, the image of this is just a finite set of points, finitely many chain recurrent classes, and phi of this is just finite set of points, and we have a Lyapunov function that orders our dynamics and says that also, okay, we have some repellers which are in the top, and we have some saddles like horseshoe that are in the middle, and in the bottom we have the attractors. So now what one can say is another kind of complexity, or the known versus unknown. So let's define the Tame diffeomorphisms as being the set of diffeomorphisms which has finitely many chain recurrent classes, and it's constant in a neighborhood of it. If it's a set of diffeomorphisms where we have just finitely many chain recurrence classes, and the same for any perturbation or small perturbation of it. And we can also, so we define the wild diffeomorphisms as the complement of the closure. So if we have a wild diffeomorphisms, it has infinitely many change recurrence classes, and almost any perturbation of it also has infinitely many change recurrence classes. Great. So let me give you some wild examples. Newhouse in the 70s proved the following, that there exist open sets of diffeomorphisms, C2 diffeomorphisms of compact surfaces, and a residual subset R of U such that any F in this residual subset has infinitely many things or infinitely many periodic attractors. So in particular, any F in this, it has infinitely many change recurrent classes. Any periodic attractor or any things is itself a change. The orbit is itself a change recurrent class. So how he did it? So he takes the original horseshoe that we have, and he pushed these legs to have a tangency here. And what he proved is that if we also move a little bit this up, what it happened is, although these are Cantor set of lines, and this is a Cantor set of lines, if these two Cantor sets were thick enough, when we push this up, we will always have a tangency. Here we have the expert, Google, and what happened is that when we have two Cantor sets and they are thick, when we move to this, although they are Cantor sets, they always have a point in common. This is very strange, but this is what Newhouse did. So in particular, what happens is that in this neighborhood U, we always have a tangency between the stable manifold and unstable manifold of a hyperbolic set. And this in particular implies that the set of hyperbolic diffeomorphisms cannot be dense in the space of C2 diffeomorphisms of surfaces. So what I want to say is that this was an example. Newhouse constructed these examples to show that hyperbolic diffeomorphisms is not dense in the space of diffeomorphisms. And he also showed that when we have stable homoclinic tangencies in this set U, then we have a residual subset R with infinitely many periodic attractors. This is because when we have a homoclinic tangency between a periodic point, we can perturb it to obtain a periodic attractor, but
provided we contract that.
okay, sorry, yeah. There is some conditions here of dissipativeness of the periodic point or the basic set, but otherwise you can have infinitely many periodic repellers. Thanks. So let me also give another wild example, which is by Lorenzo Diaz and Christian Bonatti. So they showed this kind of Newhouse phenomena in dimension greater than 2. It holds in any dimension, in any manifold, in any dimension. And it also holds in the C1 category. And also has a very strange property which is called universal dynamics. And so this is the way that they did. Here we have two periodic points, here and here. Here, this one has a stable manifold of dimension 2 with complex eigenvalue, and one unstable manifold. And this periodic point here, or this fixed point, has an unstable manifold of dimension 2 with an unstable, with a complex eigenvalue, and one stable manifold. And we have an heterodimensional cycle between these two. So, and we have here we have a heterodimensional cycle, and they managed to prove that no matter if we perturb the system, we will have a heterodimensional cycle. This figure, although this is non-transversal, they managed to prove that for any perturbation we have like an heterodimensional cycle. These 2 points, what I mean is that these 2 points are in the same change recurrent class for any perturbation of F. Okay? There is also some conditions on these periodic points. But what happened is here that, so here since we have a complex eigenvalue here, which is unstable, and a complex eigenvalue here, which is stable, the chain recurrent class that contains these 2 points, which is non-trivial, it has no invariant direction. There is nothing like hyperbolicity. There is no invariant direction. And there is plenty also of homoclinic tangencies here. Because of this intersection, the unstable manifold of this one will start going around this one, will be like this, how do you say, spiral. But we have like a cylinder over this spiral curve. And so by a perturbation of this, we will have homoclinic tangency. So by doing this construction, they managed to prove that they can have in any neighborhood of it infinitely many periodic attractors and periodic also repellers. But it also has some universal dynamics, which is the following. Take your favorite generic map on the ball, the unit ball. Then this dynamics that you want in this ball, you will have it in a generic perturbation of this system. You will find a ball that will be periodic, and after it gets to the same place, after the period, you see the diffeomorphisms that you choose on your unit ball after rescaling. So this is, in some sense, the dynamics of a diffeomorphisms, which this kind of picture. In a neighborhood of it, we can see any dynamics that we want. So this is why it's called universal dynamics. So it's really a beautiful result. So we have seen some wild examples where we have infinitely many change recurrent classes. Of course, we have also Tame examples. The Tame examples, for instance, are the hyperbolic system, where we have just finitely many change recurrent classes. But let me also give you another one, which is called Magnier derived from Anosov, which says the following: it starts with a hyperbolic matrix with integer coefficients and with eigenvalues lambda s, lambda c, which are less than 1, and lambda u bigger than 1. So if we consider this map as an automorphism of the 3 torus, we have 3 invariant directions: the one that corresponds to this eigenvalue, the one that corresponds to this eigenvalue, which is called central, and the one that corresponds to the lambda u, which is the unstable bundle or direction. And what Magnier did was, here we have x point, 0, say, and we perturb or deform our linear map A in a neighborhood of it to make that this point, which is in the central direction, it is contracting because of this eigenvalue. Now it becomes repelling, but it has to appear other 2 fixed points with this kind of picture. So this is what Magnier did. And he obtained a diffeomorphism on the torus T3, which is partially hyperbolic. That it means that we have 3 invariant directions: the stable, the central, and the unstable, like A. The thing is that we don't know what happens now to EC. We don't know that if contracts or not. And what Magnier also showed that this diffeomorphism is transitive, so it's just all the manifold is just one recurrence class, and any small perturbation of it, it's also transitive. So this diffeomorphism F has one change recurrent class, which is the whole manifold, and any perturbation of it has the same property. But it's not hyperbolic because we have points, periodic points or fixed points, we have different index, and this cannot be in a hyperbolic change recurrent set. So now let me say that Tame systems are becoming known. We are starting to understand the structure of these Tame systems. They are the hyperbolic change recurrent classes that we do understand, but there are other ones, like the Magnier examples, that we start understanding them. They have some partially hyperbolic structure. They have, we are looking for the invariant measures that they have. They have the entropy is constant. There are many results, and there are many results by many different people. We should start with Abdennour, Bonatti, Crovissier, Diaz, Gourmelon. So there are many people that has worked in this area. I'm sorry, I apologize, I could not give the complete list of contributors to this field, but what is important is that Tame systems are becoming known. So we have here a conjecture of Christian Bonatti that is it's an extension of the Pallis conjecture. That says that far from homoclinic tangencies, Tame diffeomorphisms are dense. In some sense, what it means is that homoclinic tangencies and cycles are the responsible for the wild dynamics. So here we have wild and tame, And what it says that far homoclinic tangencies, tame diffeomorphisms are dense. So what are the results in this direction? We have a result with Sylvain Crevissier, Enrique Pujals, and myself that says that if we are far from homoclinic tangencies, and this is in the C1 category, the Newhouse phenomena does not exist. I mean, if we have infinitely many periodic attractors or repellers, and this is in a robust way, then we have a homoclinic tangency. In other words, if the diffeomorphisms is not approximated by systems having a homoclinic tangency, then the Newhouse phenomena does not exist. There is another result we did with Sylvain Crevissier and Dawei Yang, is that also far from homoclinic tangencies, we have some structure on the chain recurrent set or the chain recurrent classes. I don't want to be very explicit, but it's we have this kind of structure that is the tangent bundle of the chain recurrent set splits into this partially hyperbolic structure, so which is invariant under df. So we have an unstable direction and many central directions which are of dimension 1 and an unstable direction, but the stable and unstable could be all trivial.
You may have persistently a periodic class.
Persistently?
A periodic classes. Like
Well, it can happen, I don't know. We don't know. And so what is important when we have this structure is that this structure persists for perturbation. Any diffeomorphisms nearby will have the same kind of structure. And this might help to understand the dynamics. So this is some contribution, but still we are far from saying that far from homoclinic tangencies, we are in the Tame class.
That composition is orthogonal?
Huh? No. You may change the Riemannian metric to make it orthogonal, but no, it doesn't matter because this is continuous, so we could be also almost orthogonal. But if you define it to be always orthogonal, maybe your Riemannian metric is just continuous. But, So what about attractors and quasi-attractors? So let me define that a compact set lambda is an attractor if it is transitive. It's a transitive set. It has a dense orbit and attracts a neighborhood of it. Open set U, so that when we map it and take the closure, it is contained in U, and any point in U will converge by forward iteration to lambda. A quasi-attractor is a set which is a change recurrent class, and there is a family of open neighborhoods UN such that these neighborhoods are, we have a sequence of attracting neighborhoods of lambda. The thing is that Conley's theory is that quasi-attractors always exist. But what about attractors? And this goes back to a question of René Tome, that if attractors exist generically, indeed, so this was a question, or this was a question of René Tome, and then Pallis and Pugh listed in the some 50 problems in the 76, and they put it as a conjecture of René Tome. If two attractors exist generically, and indeed, what we have is that in dimension 2 for C1 generic diffeomorphisms, attractors do exist. And moreover, there exists a hyperbolic attractor. So for a C1 generic diffeomorphisms on compact surfaces, there exists a hyperbolic attractor. Araújo was a student of Ricardo Mañá, and this was in '86 or something like this. But recently, Christian Bonatti, Lee, and Dawei Yang gives a counterexample of this in dimension greater than 3, greater or equal than 3. If you have a manifold M with dimension greater or equal than 3, there exists an open set U of in the C1 category, and such that CR generically in this neighborhood, no F in this subset R has an attractor. It has quasi-attractors, but they are not attractors. Okay. So this is a very...
For any R,
For any R, yeah.
R equal
1, 2, 3, whatever. Whatever you want. Yeah. You don't have... So CR generically, attractors might not exist. But here we have, what about far from homoclinic tangencies? There are some results. Here is a result from Bonatti, Ganli, and Dawei. Oh, sorry, Dawei is not Yang. Here is Dawei Yang. That's far from homoclinic tangencies. The quasi-attractors that we always know that exist are isolated from each other. They cannot accumulate it on itself. And also, where we have a result with Sylvain Raphael Potier, that far from homoclinic tangencies, there are finitely many quasi-attractors. So these quasi-attractors should be attractors in this setting, far from homoclinic tangencies. Quasi-attractors should be attractors, but this still don't know. So let me say something about the tools that we have used in all these kind of results. And the important thing here is that why we did it in just the C1 category, because we just known some perturbation techniques in C1. The perturbation techniques that we have here are not known to be C2, how to do it C2. So there are some orbit perturbation techniques to obtain periodic points or so wherever. That is called, for instance, Puke closing lemma, Magnès-Ergodic closing lemma, Hayashi connecting lemma, Bonatti-Crevisier connecting lemma for pseudo-orbits, and so on. So these are results or techniques to perturb the system and obtain some property that we want. For instance, we have a recurrent point. We can perturb it to obtain a periodic orbit. Magnès-Ergodic closing lemma is an extension of Puke closing lemma, but from the ergodic point of view. Hayashi connecting lemma is another result that says how to connect 2 points, how we can perturb that 2 points will be in the same orbit, and so on. There is also a result which is called Frank's lemma, which is something to understand how we can perturb the derivative in the C1 category. Also, how to create some conditions to create tangencies. This is something that we did with Enrique and was extended by Lanwen and then by Nicolas Cook-Melon. Magnet's ideas from the stability conjecture. There is some very nice notion of blenders created by Lorenzo Diaz and Christian Bonatti. And there are many other things that will be impossible to list here. So, but let me also say some strategies to how do you prove this kind of results that we mentioned before. The first thing is that if we are far from homoclinic tangencies, we have dominated splitting. We have a splitting like this, like in the hyperbolic setting, but the thing is that we don't know the behavior of E or the behavior of F. In the hyperbolic setting, you know that these along vectors in E are contracted by the diffeomorphisms, by the tangent map in the future, and for this are contracted in the past. But here we don't know. The thing is that we can decompose this in invariant, and this splitting is robust. I mean, any perturbation of it, you cannot destroy this structure on the tangent bundle. So once you have also dominated splitted, you can extend it to have, if you look to the finest dominated splitting that you have, it is like this. You have a stable and a bunch of central ones which of one dimension and a stable one. But this could be trivial. So what's the fact about this? When we have this kind of decomposition, this is that that allows us to split the dynamics in invariant directions. Like in the when you have a linear map and you have two subspaces that are invariant, then you can split the dynamics of the linear map as the dynamics on these linear subspaces. So this is what we have here. We can split the dynamics in some subspaces, and what we know is that the ones that are not stable or unstable, they are one-dimensional. So we don't know what happens with the points in these subspaces, if they are expanded, contracted, or whatever. But at least we can split it like this. And what we proved with Sylvain Crevissier and Enrique Pujals is that the ES and EU are not trivial. That if we have a dominated splitting like this, with F, which is one-dimensional, that F should be uniformly hyperbolic expanding. So this means that in this decomposition that you have here, the stable is not trivial, and the stable and this one is also not trivial. But what about the middle ones? The middle ones, they are very difficult to understand, but Sylvain Crevissier developed a tool which is called today Crevissier central models to understand the dynamics from this decomposition. But, so the thing is, we split the dynamics in this kind of one-dimensional dynamics, see? But, so This should be very understandable and simple, but it is turned out that it's not very easy. So summarizing what we have is that we have homoclinic tangencies where we have a homoclinic tangency and the homoclinic tangencies mixes the directions, and far from homoclinic tangencies, we have this kind of a structure, and this should implies that we are in a simple case like Tame dynamics. But still we don't know. To see how tricky this could be, let me propose a basic problem that if we have a partially hyperbolic diffeomorphisms, we have stable, central, and unstable, central of dimension 1. Is it true that any generic perturbation of F is tame? Maybe F, you can construct examples where F may have infinitely many chain recurrent classes, but the thing is that can you perturb it, or an arbitrary generic perturbation made it tame, or this is just an example of the above. What if F is the time one map of an anosov flow? This is a very simple problem that we don't know how to answer. Or also if F is the product of an anosov times the identity on S1. So thank you very much for your attention.